Hello aspirants, welcome to Forest Study. My name is Debdeep and this is a brief introduction about me which is listed here. Now I'm excited to share a very important update with you. So until now we have been offering our geology course in the form of comprehensive PDF notes which have helped numerous aspirants score exceptionally well in the geology optional for both the Indian Forest Services as well as civil service examination. In fact, our students have scored over 240 marks in the geology optional for IFoS. So starting this year, we are very proud to launch our online classes for geology. Based on the success of our notes, we are confident that these classes will set a new benchmark in quality and effectiveness. And our approach will not only focus on simplifying complex geological concepts through clear and concise teaching, but we will also try to provide powerful mnemonics and memory aids to help you retain information in a better way and recall it effectively during the exam. As we all know that geology can be a challenging subject to remember, but with our innovative teaching methods and refined pedagogy, we aim to make it both accessible and engaging. I would like to conclude this introduction that join us to strengthen your preparation, score high, and take a confident step towards your dream service. So today I have decided to discuss structural geology, specifically folds, because maximum questions come from structural geology, especially folds and faults, and also this is a favorite for most of the students, as I know, as the topics are very interesting to learn. So let me just switch tabs. Okay, so folds. What are folds? Folds are bends in rock layers that occur due to compressional forces. So one thing is clear, that folds form due to compressional forces. So what happens is, let me bring out the whiteboard and I'll explain it better. So this is a very simple concept. Say for example, if I have layers like this which are formed due to constant sedimentation around us. So sediments are falling here, and these are layers that forms due to sedimentation and hardening and form rocks. Actually these we call our beds. Now if we have compression like this will form bulging of the layer, it will form folds. This is a simple concept how folds are formed, right? Now coming back to our slide. Now for a fold we have different like nomenclatures to define a fold. Like defined paths are named. For example, the axis of a fold or the hinge, it is the line of intersection between the axial plane and the fold surface. So this is the fold surface, right? And this is the axial plane. Axial plane is a plane which cuts the fold into equal halves. Okay, so here's a definition of axial plane also. An imaginary plane that divides the fold into almost two equal halves, right? And you can see that there are two limbs also. From the axial plane there occurs two limbs, limb 1 and limb 2. The sides of the fold that are relatively less curved compared to the hinge. So these are less curved than the hinges, right? And also this is the crest, that is the top part, highest point on anticline. This is called an anticline. This is called a syncline. Which is convex upward is called an anticline. which is convex downward is called a syncline. So trough, as we know, lowest point on syncline. Okay. Now amplitude and wavelength. See, this is a 2D diagram of a fold or a curve. So this is the amplitude. Amplitude is the vertical distance, right? Vertical distance between the crest or trough and the hinge line. And for wavelength, wavelength is the horizontal distance. The horizontal distance between two successive crests or troughs. So these are two successive troughs and these are two successive crests. Okay. Now plunge. Plunge is the angle between the hinge line or axis of the fold and the horizontal plane. Okay, the angle between the hinge line, this is the hinge line, these are all the hinge lines. Okay, so hinge line or the axis of the fold and the horizontal plane. Okay, the horizontal plane, it makes angles. Let me draw it pretty quick. Say for example, this is a fold, right? This is a tilted fold, not an upright fold. So if we mark a horizontal here, and this is a hinge line, or it can be called a fold axis also. So this angle is called a plunge. Okay, plunge. Fine. Now the interlimb angle, the angle between the two limbs of a fold. It is very simple. The angle between two limbs of a fold is called interlimb angle. You see, this angle will be called an interlimb angle. Now there are a lot of classification of fold, of how folds are classified on the basis of different parameters. So the first parameter will be tightness. Okay, so based on tightness of a fold, the fold can be classified into 5 classification: gentle fold, open fold, close fold, tight fold, and there is isoclinal fold. Now, how will you remember this? There is a quick technique that I'll share with you. Okay, so you will remember it as GOCT, right? GOCTI. G for gentle fold, O for open, C for closed, T for tight fold, I for isoclinal fold. GOCT. You will have to remember this code and you will be able to classify the folds on the basis of tightness, right? Now, you have to start with angle 180 degrees. Okay. Now, so 180 minus 120 is 60 degrees. So from 180 degree to 120 degree, you will have gentle fold. If the interlimb angle between the two limbs is in between 120 to 180, it will be called a gentle fold. If it is from 70 to 120, it will be called open fold. If it is from 30 to 70, it will be called a close fold. From 0 to 30, it will be called a tight fold. And if the limbs are nearly parallel, then it will be called isoclinal fold, in which the interlimb angle will be 0 degrees. Okay. So how will you remember this? You will start with 180. So 180 minus 120 will be 60 degrees. 60 degrees will be there in between. Here it will be 50 degrees. Here it will be 40 degrees. Here in tight fold it will be 30 degrees and 0 degree. So 180 degree minus 60 will be 120 degrees. 120 degree minus 50 will be 70 degrees. 70 degrees minus 40 will be 30 degrees. 30 minus 30 will be 0 and then 0. So you will remember it like it's an stepwise: 0, 30, 40, 50, 60. Like this, you will have to remember the values. Now, how are these formed? Gentle fold, as we said, this is not so tight, right? So it will form under mild compression. Indicates broad tectonic uplift or subsidence with limited deformation. This occurs in a regional level, right? So broad open folds in sedimentary rock sequences. Now open fold are moderate compression. Like the compression is more with respect to gentle fold. And form compression in shallow crustal condition. It often occurs in the shallow crust of the earth, like in the upper surface of the earth. Importance are common in sedimentary basins, indicates mild tectonic activity. And examples of open folds are found in the Appalachian Mountains. Okay. Now, close folds. Close folds, 70 to 30 degree, as we have discussed. Higher compression stress, typically found in zones of crustal shortening, helps understand active tectonics and stress distribution. Example are tight folds in the Scottish Highlands. And isoclinal folds. Isoclinal folds have nearly parallel limbs. Okay, axial plane is inclined, axial plane is vertical, and axial plane is horizontal. So inclined isoclinal fold will form when the axial plane is inclined, as the name suggests. Vertical isoclinal fold will happen when the axial plane is vertical. And recumbent means that the axial plane is in horizontal position. That means we will have a recumbent isoclinal fold. So two conditions should meet. That is, the axial plane should be horizontal. Also, the limbs should be parallel to each other and have a 0 degree, nearly 0 degree interlimb angle. Then we will call it a recumbent isoclinal fold. Okay. Recumbent, these isoclinal fold form extreme compression because they are near to each other, like they are very parallel. Okay. So extreme compression, high grade metamorphism rock. Metamorphism occurs in not in the crustal surface but below it. It needs higher pressure and temperature to have metamorphism in effect. We will study these in the later classes. What are the importance? So marks area of significant crustal shortening, typically linked to large scale orogenesis. Orogenesis means mountain forming, mountain building, it says. Example, isoclinal folds in highly deformed metamorphic rocks. So mostly these isoclinal folds are found in the metamorphic rocks. Okay. Now, apart from that, there is also orientation of axial plane. This orientation of axial plane and orientation of fold axis. Fold axis is this one. This is the fold axis. This one is the fold axis, which meets two crests is called a fold axis. Okay. Or this can also be a fold axis which meets two troughs. So based on axial plane, and later we will study that based on fold axis also we can classify folds. So these two are very hot topics in UPSC examinations. Questions have come. Questions have come in past years also. Like in the last, I think in 2020, they have asked to classify folds on the basis of axial plane and fold axis. So I think there is a high chance in 2025 that they will repeat the question. So okay, so on the basis of axial plane, we can see that symmetrical or upright fold. Symmetrical upright fold, as the name suggests, both limbs dip at equal angles from axial plane, but in opposite direction, like this. Symmetrical upright means it will be vertical. The axial plane will be vertical. Okay. The axial plane is vertical, passes through the crest or trough, depending on anticline or syncline. The limbs are mirror images of each other. As we can see here, they are mirror images. No one is shorter than the other. Both are of equal length. Uniform compressional force. Uniform compressional force should be there so that there is no asymmetricity in the fold. Indicates balanced stress condition and uniform tectonic movement. Symmetrical folds, sedimentary layers. So as I can say, the symmetrical folds are very rare to find in the nature because the tectonic forces are not always symmetrical. Most of the times it is asymmetrical in nature, and that's why it forms asymmetrical. A little bit asymmetry will always be there in a fold that is found in the Earth's crust. Okay, now asymmetrical folds. These are the widely accepted and widely found folds. So definition: limbs dip at unequal angles in opposite direction. One limb dips more steeply than the other. So as you can see, this limb is lengthier than this one. This is a shorter one, shorter asymmetry. The compression from left is more than that of the right. That is the reason that the compression is not uniform. That is why this shape is also not uniform. Characteristic: the axial plane is inclined and does not necessarily pass through the crest line. There is an inclined axial plane. See, there is an inclination. The limbs are mirror images. One side is steeper. Formation, unequal compressional force or shear. See, unequal compression force or shear. Importance, useful in determining shear zones and stress gradients. Example, inclined folds in the Swiss Alps. So what is this shear zones? Let me explain it in our whiteboard again. Say this is a mountain and this zone is a shear zone where shearing is happening. Shearing means opposite compressional force makes it shear. So since this force is going like this and this force is going like this, so there will be shearing. So the layers will ultimately form like this. And you can see the axial plane is tilted, not vertical, right? Simple, right? Okay. So where are we? Yeah, asymmetrical folds. Useful in determining shear zone and stress gradient. Inclined folds in Swiss Alps is an example. Now, overturn folds. Definition: one limb is pushed over the other, resulting in a steep dip. See, the dip of both the limbs is different. This one is steeper, this one is a gentle one. Okay, so you will see that when one limb is pushed over the other, it should be like this, right? But it came like this. So both the limbs are dipping in the same direction, but the dip amount is different, right? The dip amount of this limb is different, the dip amount of this limb is different, but both the direction of the limb or direction of the dip is same, that is towards the left hand side. The axial plane may be significantly tilted. One limb dips at a steeper angle, often exceeding 90 degrees. 90 degrees means this 90 degree it will exceed and cross, and then both will dip in the same direction. Formation, intense compression leading to one limb folding over the other, indicates thrust faulting and major tectonic deformation. Examples are overturn folds in the Himalayas. Then there is recumbent fold, as we have discussed here. Recumbent, right? Recumbent means the axial plane will be horizontal, nearly horizontal. Folding is so intense that both limbs become almost horizontal. This happens because of shearing, as I have explained in the diagram. Um, Characteristics: axial plane is horizontal, often formed under extreme compressional forces, typically indicates significant crustal shortening. Crustal will short because crustal shortening means, say, crustal shortening means, what is crustal shortening? Say example, we have a crust like this. This is the Earth's crust. It's of, say, thickness A and have folds like this. But if we see folds getting recumbent like this is the axial plane, say. Okay, this is the axial plane, and it is getting recumbent like this. This is a 3D view of the fold. Okay, so the height decreases, right? It should have been like this, but now it is like this. So this is called crustal shortening. This much amount it has shortened, right? This much amount it has shortened. So this is called crustal shortening. We will learn more about it in tectonics class. So recumbent folds are often found in extreme horizontal compression or crustal overburden associated with nappes. Nappes actually thrusts, okay, in orogenic belts, again mountain building process, making significant tectonic activity. Okay. So this is all for recumbent folds. Example of recumbent fold is in Rocky Mountains. Now coming to the classification based on inclination of the axis, or you can say inclination of the fold axis. This is also very important, comes a lot in exams. So always whenever you are writing the mains in geology, always try to draw as much diagrams as possible. Like 90% of your answer should have diagrams. Even if it's a simple one, you should draw. Okay. uh, Diagrams as well as examples are must in mains. Okay. You should draw, like for example, if you are defining classification based on inclination of axis, and you're saying horizontal fold, plunging fold, and vertical fold, you should draw diagrams for each of the fold, not one. Okay. All the fold you should draw. Okay. So first one is horizontal fold, which is non-plunging. So fold axis is horizontal. Formation, gentle compression or uplift. Common in undisturbed basins, reflects tectonic stability. Horizontal folds is undisturbed sedimentary sequences. So let me draw it, and then I will explain all the three: horizontal fold, plunging fold, and vertical fold. Okay. So this is a fold, and this is the fold axis. Okay. So if this fold axis is horizontal, then it will be called a horizontal fold. If I'm again drawing a fold, just like this. If this is having an angle, certain angle, say 30 degrees, then it will be inclined fold. If a fold is like this, this is 90 degrees, right? So this is a vertical fold. Horizontal fold, inclined fold, vertical fold. As simple as that, on the basis of fold axis. This is a fold axis. Okay. So horizontal fold is non-plunging, plunging fold or inclined fold, vertical fold. Okay, so what is plunge? This angle is called plunge. Okay, plunge. This angle is called plunge. Plunge of a fold. The angle between the horizontal and the fold axis is called plunge. This is a incline or plunging. You can say plunging fold, horizontal fold, vertical fold. Okay. So horizontal fold, which formation, gentle compression or uplift, common in undisturbed basins, reflect tectonic stability. There is tectonic stability to have required to have a horizontal fold. And horizontal folds is in undisturbed sedimentary sequence. There is no disturbance, just simple compression. Then it will fall. It will form horizontal folds. Now plunging fold. Now it is oblique in nature. That was due to oblique compression. Importance: useful in identifying structural traps for hydrocarbon. Plunging folds are very useful. It forms Plunging folds forms actually basin where hydrocarbons are found, like petroleum deposits are found. Okay. Example: plunging anticlines and synclines in Appalachian mountains. And then there is vertical fold. Vertical fold is, I would say, it's uncommon. Intense compression force, often in high strain zones, common in collision zones, and highlights strong tectonic deformation. Example: vertical folds in highly deformed terrains. Okay. So these are simple, right? Horizontal, plunging, and vertical. Plunge means, I've just said earlier. And there are some classification which are miscellaneous, right? There is no certain parameter, and they are found in nature. So first one is chevron fold. Chevron fold have actually sharp hinges and straight limbs, like this. Characterized by sharp hinges and straight limbs, formation often forms in brittle deformation in layered logs with alternating competency. What is this alternating competency? Alternating competency means these are competent rocks and white ones are incompetent rocks. when there is a alteration between, say, sandstone and shale. Sandstones are brittle, whereas shales are not. Shales are a little bit ductile. That means they will bend, whereas sandstone will break. So this happens when there is an alternate layering in the earth's surface, say sandstone shale, sandstone shale, sandstone shale, like this. And then there is a compression and forms a fold. Then it can form chevron folds, brittle deformation and layered locks with alternating competency. Importance. Common in sedimentary sequences, as I said, sandstone and shale sequence indicates tectonic stress variations. Example are chevron folds in sedimentary rock sequences. Now, a similar kind of fold also you can say, but are rarely found in large scale, which is called king fold. So what is the major difference between a king fold and a chevron fold? Both are angular in nature. But let me what is the difference between a king fold and a chevron fold? So a chevron fold will be like this. When you are drawing it in paper, you will draw one a little bit less angular and one very sharp hinge, then angular, sharp hinge, like this. Whereas in king fold happens like this. Everything will be very sharp, no angular or little bit rounded, nothing. All will be sharp. This is the actual plane. This is king fold, and this one is chevron fold. Now how will you remember it? See, chevron, C. C means, you can see this is a C. So there will be a curved one and then a hinge. एक आपका rounded रहेगा, एक आपका angular रहेगा, एक rounded, एक angular. Whereas in kink, you will see K means there is a sharp angle here. So everything will be like K, sharp. Okay, so you remember like this: K for kink, C for chevron. Chevron will have one alternate sharp and little bit rounded hinges, whereas in kink all hinges will be angular. Now we have done with chevron fold. Let's come to box fold. Box fold have two axial planes forming a box-like structure like this. This is two axial planes. Okay. Formation: differential stress acting at 2 points on a layer. Importance: indicates localized compressional forces common in coal basins. So in coal basins we can find box fold. See, coal, CO, box, BO. Coal and box. So remember it like this: coal are stored in boxes, so box fold have common in coal basins. Example: box folds in coal seams. You can name any coal mine you have visited or you have and that will work, because in maximum all the coal mines there is a possibility of the box fold. Okay. Now dome and basins. So dome and basins. What are dome and basins? Dome is an anticlinal structure, that means convex upward. Basin is a synclinal structure. So if you have seen a कढ़ाई, कढ़ाई होता है ना, कढ़ाई. So कढ़ाई को अगर आप cook करेंगे, like if you are cooking in a कढ़ाई, that means the concave part is upward, so that is a basin. If you flip the कढ़ाई, अगर आप उसको उल्टा कर देंगे, then you will see the convex part is upward, so that is a dome. Okay, simple explanation for that is dome and basin. So basin, as you can say, you don't have to remember this Michigan basin and Black Hills. You will just you can name any Ganga basin, Godavari basin, Pranita basin, Krishna, Godavari, anything, Yamuna, not Yamuna, only Ganga, sorry. Ganga basin. You can give example of Ganga basin here. And dome, you can see kadai, when you cook, it will get darkened, right? उसमें काला पड़ जाता है, right? So when you are cooking in a kadai and काला पड़ जाता है, तो उससे आपको याद रहेगा the example Kala Dongar. Kala Dongar is a dome which is found in Gujarat. Okay, Kala Dongar. Kala Dongar is a dome which is found in Gujarat. Now, fan fold. Fan fold or upright fold where both limbs are overturned. See, a fold should be like this, right? But it has gone overturned, and the inclination negative interlimb angle. So interlimb angle is negative, right? It should be like this. Here the angle should be like this, but it has like this, reversed, right? So negative interlimb angle. In anticlines, limbs dip towards the axial plane, right? And while in synclines, limbs dip away from the axial planes. So fan folds have negative interlimb angles, crest and troughs are rounded, formation intense compression leading to limb overturning. Found in areas of extreme deformation, helps in analyzing compressional regimes. Okay, definitely compressional regimes, because this is a fold are always found in compressional regimes. Okay, now what is a monocline? Monocline is a local warping in horizontal strata. Say there's a horizontal strata and there is somewhat a compression, so this will form a step-like manner, and this is called a monocline. If you have visited Himalayas or any like maybe Himachal Pradesh and Uttarakhand, you will see a lot of monoclines from highways. So local warping in horizontal strata formation, localized warping due to faulting or igneous intrusion, important, indicates subsurface structures like faults or magma chambers. The homocline, beds dip uniformly at the same angle in the same direction over a large area. So what is a homocline? So I think there is no picture of homocline, but beds dip uniformly at the same angle in the same direction over a large area. So if you see a large area where the beds are continuously dipping in the same angle, that means there is no disturbance in the area. We can say that it's an homocline. Okay. Seen in extended dipping strata, how it's formed, uniform tilting due to regional tectonic uplift or tilting. It should be regional tectonic uplift where there is no disturbances otherwise. Useful in reconstructing the sequence of regional deformation. Okay, structural terrace. So local flattening in an otherwise uniformed dipping belt is called a structural terrace. See, initial dipping was like this, but then it turned. So local flattening in otherwise uniform dipping belt. So say for example, this is a bed and it was compressed like this, vertically compression. So it formed a fold like this. That will form a structural terrace. Structural terrace has resemblance with this monocline. Don't get confused, okay? This is like horizontal, then dipping, then again horizontal. But in a structural terrace, it will be vertical, then horizontal, then vertical. Okay, so draw your diagrams very carefully. Formation. Flattening caused by changes in stress or sediment deposits. Okay, so if I how it is formed, let me explain it to you. Say say this is a normal inclined bed, right? If we have crustal shortening like this, compression here, this will form like this. This will form like this, right? Due to compression. Okay, this will be called structural terrace. Okay, represent period of tectonic sequences and accommodation during crustal deformation. Now, parasitic fold. Parasite, as the name is similar to you, parasites are often organisms that host upon a another organism where they get their food from, right? So parasites folds are small secondary folds that develop on the limbs or hinges of larger primary folds. So these are actually parasitic folds. Okay. These are smaller scale folds on a large regional fold. So what happens actually is, for example, um, say we have a layer, then it got folded like this, and then again it got compression, and say for example it is consisted of a lot of layers in between it, which has a different competency. That means it has a different ductile nature in it. So in that overall regional fold, you will find, due to this compression, you will find like this. Okay. In the left hand side of the limb you will find it Z fold, and in the right hand side you will find S fold. This will look like S, right? This looks like Z fold. This looks like S fold, S fold, S fold, Z fold, and this one looks like what? M, right? So M fold, Z fold, M fold, S fold. Okay. So parasitic folds are smaller secondary folds that develop on the limbs or hinges of large primary folds. They typically reflect the same deformation phase and are aligned with the stress fields responsible for the primary folding. These folds are often asymmetrical, with their orientation determined by the larger fold symmetry. As you can see, these folds are asymmetrical. That means one limb is shorter than the other. Importance of parasitic folds. Parasitic folds are, see, in the outcrop section, that means in the field, we geologists don't get the full outcrop of a fold. So we find indications where a fold can form and how the fold is by smaller indications that are found in the fold. So one of them is this parasitic folds. With these parasitic folds, for example, if we are getting Z fold somewhere, so we can say this is the left limb of a fold, right? If we are getting S fold somewhere, it's anti-clockwise local versions, then we will say this is the right limb of the fold. And also if we are finding M folds or W folds, then we can say that we are at the crest or trough of a fold. Okay. So importance of parasitic fold. Uh, Indicators of larger fold geometry. This, in the parasitic fold, wherever it is found, it indicates that there is a regional fold somewhere, right? The sense of asymmetry in parasitic fold helps determine the hinge zone and geometry of large fold. Tectonic stress analysis. Parasitic folds record local variations in stress and strain during deformation. There's local variation. Okay. Determining facing direction helps geologists identify the stratigraphic sequence and folding direction in complex terrain. Just like I told before, like Z fold and S folds are very important to know which one is top, which one is bottom, which one is left, which one is right, which limb we are looking upon. Okay. So reconstruction of fold history provides insights into the progressive development of folds and deformation of faces. As just I have told you that this regional fold has formed first, then the micro parasitic folds have formed. So using this and a lot of other tools, we analyze these folds and we get to know how the stress and strain has changed over time and form this ultimate result. Now, exploration significance assist in locating mineralized zones associated with folding, as parasitic folds often contain mineral-rich shear zones. These, since I have told you that there's a competency contrast between the layers. That's why this has folded. See, this has folded. This the say the wavelength is much more than this one, right? So this, because this is more competent than this one. So different mineral deposits are also found in this type of zone. So GSI and a lot of if you are a forest officer, also you will get collaborations with GSI to find minerals in zones, because these folds are often found in forest areas. Okay. Mm, okay, now parasitic folds. Smaller folds on the limbs are larger folds, as stated above. Example: parasitic folds on the flanks of major anticlines or synclines. Okay, so if someone if a question is asked about parasitic fold, definitely draw this diagram and then label it properly. Okay, now uh, drag fold. Okay, so drag fold is a fold which is consist of a mechanism of folding, also a mechanism of faulting. So both compression as well as extension is required to form a drag fold. Okay, composed of both folding and faulting activity. What it is, they are combination of both folds and faults. Where they occur, they usually occur at plate boundaries, and they occur usually occur in plate boundaries where there is a, we will discuss about plate boundaries later on, but for this class you should know that transform fault or like strike slip fault, which the plates which go past each other usually forms drag faults. So these are minor asymmetric folds which with major folds, but confined only to incompetent bits that are sandwiched between competent layers. So there should be a competency contrast between the beds of the previously formed fold to form a drag fold. Okay, for drag fold to form, there should be a previously formed fold due to compression. Then there should be a fault that has happened due to extension that will result in the formation of a drag fold. Okay. These develop due to shearing and dragging effect. As the name suggests, there should be a dragging effect or shearing effect in between competent incompetent plates and flow plastically during folding and competent bed. So the folded layer to show a dragging effect and shearing effect should have a ductile nature to it, right? Ductile nature means it should be plastic. Like if you stretch, it should stretch. It should not break. So those type of layers form actually drag folds. So the folds in incompetent beds are a result of initial build-up pressure and before breaking. Folding always occur before faulting. Like I said, first occurrence should be the folding, then the faulting will happen. During folding, competent bends slip over each other and break down without deformation, while weak and incompetent layers develop folds. Okay, so let me draw the drag fold for you. Say you are seeing a fold like this in an outcrop from the sky. Okay, so you're seeing a fold like this from an outcrop through the sky. So this is a Hawkeye view, right? This is a fold. This is a Hawkeye view. Now, for example, if we see a strike slip fault, you know what is a fault is? Fault is a breakdown of a surface, okay, or a big fracture, you can say, where two blocks slip past each other. So if you are seeing it from the sky and we see there is a fault, this will be a strike slip fault. Say this is a strike slip fault like this. So what will happen? This will form like this. This will be dragged. Okay, so if this is the fault surface, this is the after effect of the slip. This will form like this. Because of this friction and dragging effect, this will form a drag fault. Okay, drag fault. So this was drag fault. And this will be it for today's lecture. I hope you have enjoyed the lecture and found it valuable. So if you choose to enroll in this course, we will be guiding you at every step of the way, and together we'll work through your doubts and challenges to ensure a clear understanding and a steady progress. And if you are committed to cracking the exam with confidence and clarity, please join us for a study. Let's turn your dream of joining the joining a dream service into a reality together. Okay. So thanks a lot for your attention.